gold. And when you think about the fact that this soil probably took hundreds of years to form,
Hello, my name is Christine Brown. I'm a field crop sustainability specialist.
Alrighty, welcome to the final 2025 March Manure Monday. Last week we talked about compaction with my colleague Ian McDonald, and that recording, along with today's, will be posted later this week. That'll give you a full complement of the 5 sessions from 2025. So a few logistics up front. You will see a QR code for the certified education units posted at the end. You will also see another QR code, which is a KSE, knowledge sharing event. If you don't know what that is, don't worry about it. It just applies to a few that are involved in a funding program here in Ontario. So do please post your questions, your comments in the chat, but also stay muted so that we can hear the presenters. Few things, 2025's North American Manure Expo will be in Ohio, and it will be July 30th and 31st. So mark that date, plan to attend, be sure to check that out. And being as this is our final week, I do want to say a few thank yous. First of all, to Quinn Harder. Quinn is the one working in the background. He produced the video you just saw. He edits and posts the sessions and is kind of our AV host. So thank you, Quinn. Also, thank you to my partner in crime here, Christine Brown. Chris is really the brains behind this operation and really nails down the topics and the speakers. So we appreciate that, Chris. Thanks to all our speakers, by the way, who have really contributed their time and expertise. And most of all, thank you to each of you for joining us and interacting with us week by week. We do really value your feedback, by the way. If you have thoughts, ideas on topics for next year, good speakers, or other feedback, if you could please reach out by email to Christine Brown, and you will see her email posted here in the chat. All right, let's move on to today, to our final topic here, which is application strategies to maximize nitrogen and reduce greenhouse gas losses in the field. And happy to have 2 presenters here today. And joining me are Heather Darby. Heather is University of Vermont, and she is an agronomist and a soil scientist. Debbie Aller is Cornell University Senior Extension Associate, and she, in fact, is also a soil scientist. So Heather and Debbie, glad to have both of you here tonight. They're going to tag team it. Heather, you can start it off, and I'll throw the ball right to you. Take it away, Heather.
All right. Thank you. Thank you so much. Thanks, everyone, for having us be a part of Manure Monday. I'm really excited to be invited to speak here. I've attended a few of them in the past. And I think it's a great opportunity to learn from each other about all things manure. So thanks for the invitation. And today I'm going to be talking about nitrous oxide emissions from manure application, and all the different research and strategies that our team here at UVM has been looking at to reduce nitrous oxide emissions from manure. And you can see up here, I have a slide that says biochar to suppress emissions from manure applications. And that's where we're at right now, but really this will be a story that involves many people from UVM, students current and past, and myself, a faculty member at UVM, and Carol Adair, really looking for solutions, looking for some strategies, again, to reduce nitrous oxide emissions from manure applications. So probably nothing new for any of you either, but we have really been struggling with weather extremes where we are in Vermont, and I know others have too. It's been really tough over the last few years, in particular, having very, very extreme rainfall, but then also really sometimes even in the same year, kind of extreme drought. So lots of extremes going on here. And of course, farmers that I work with, and I'm sure that folks are working with all over this country, are trying to figure out how to respond to these events, trying to think and learn about new strategies to manage agriculture and cropping in the face of extreme climate. We have done, a bunch of surveys as we like to do at the university to understand how farmers in our area are responding to climate change. And this survey actually is quite old, almost a decade old, that we did. And one of the primary BMPs or strategies that farmers were looking at even a decade ago were alternative manure management techniques to basically help them retain more of the nutrients in manure, and also to reduce losses, not just for their crops, but into the environment as well. So one practice that farmers have become increasingly interested in Vermont, and we've been working on for probably 2 decades now, is manure injection. And lots of reasons for that in our area. We're in Vermont. It's a very, very small state. You don't sort of hide in the rural parts of Vermont and kind of get away from your neighbors. People are everywhere. We have very small fields, and most of even our agricultural areas have lots of people around them. And so public pressure, climate, and then environmental concerns as well have really changed how farmers think about manure application. And again, we've had a lot of growing interest and adoption of injection. And again, lots of reasons for that, both, agronomic, soil, environmental, etc. So what we've been trying to really understand is, how does this change the impact of greenhouse gas emissions? And I think, originally many of us thought that injection was an opportunity to reduce emissions as well as smell and other losses. That's what we associate injection with, versus our standard, which is standard here in Vermont, which is broadcast. As we know, nitrous oxide losses are derived, or in agriculture, derived from soil management practices, and it is a large amount of the emissions, not just from agriculture, but other industries as well. And most of the agricultural emissions are derived from soil management practices. So again, for all of us in agriculture here and beyond, we're looking to strategies to reduce those emissions, both to help with climate, but again, the bottom line too. So where is nitrous oxide coming from? And not to spend too much time on this, but comes from bacteria that are living in the soil that are also just trying to survive. They get their energy from eating nitrogen and other compounds in the soil. And generally those bacteria that produce nitrous oxide, they're in the soil, but they're more prominent under saturated soil conditions. Right? So when soils are relatively dry and oxygen is available, microbes will oxidize ammonium into nitrate for energy. And during this process, and again, we don't know a ton about this, but we do know during this process there is some nitrous oxide released, but it's a really, really small amount. But then on the other hand, when soils are really wet and oxygen is low, most of the nitrous oxide comes from a process that most of you here know called denitrification, where the microbes use nitrate to oxidize carbon for energy. And generally, it's thought that most of the nitrous oxide in agricultural systems comes from denitrification when soils are wet, or at least where there's lots of microsites in the soil that are wet. So obviously in these very wet years that we've been having, we know that we're seeing a lot of nitrogen losses to denitrification. Okay, let's get all my little, oh, there we go. Forget about all these little animations I have in here. Okay, so this whole process depends on a lot of other items too. So both need available nitrogen. Nitrification needs ammonium, and we know that manure provides this. And denitrification needs nitrate. Nitrification or chemical fertilizer provide this, right? But only for denitrification do we need available carbon for the microbes to eat to get energy. So you can see where adding manure into our systems can increase nitrification, but can also increase denitrification. All right. So when manure injection inserts liquid manure into cuts in the soil, it likely increases nitrous oxide emissions by increasing soil moisture and also adding carbon and nitrogen below ground where the soils are wet and where microbes can quickly denitrify. So basically, we're concentrating all the things, the items that these bacteria need to denitrify that nitrogen, right? We are removing oxygen when we pump that manure into that slot. We're creating a lot of moisture. So it's becoming even more anaerobic. And then we're adding a really good carbon and nitrogen source to the system. So that in itself is increasing denitrification when we use manure injection. All right. So we've been looking at this closely. There's so many reasons for injection that are beneficial to the farms, to communities. There's less smell. There's more, hopefully, retaining nutrients for crops. So a lot of benefits here. And really our goal was, to figure out how to reduce that. All right. So we first started by just showing in our communities. So our first hypothesis was, will manure injection increase nitrous oxides emissions beyond broadcast? So first we wanted to make sure that this was true, that this was potentially an issue that we should be dealing with, and especially under our climate and farming systems. So we went out into the field, and here's some of our general methods that we were using to measure nitrous oxide. And we've used this in all of our experiments, but essentially measuring every two weeks, and often more frequently after events, whether that's manure application, possibly a heavy rain, or fertilizing applications, and during the growing season or when the temperatures were above 4 degrees C. So our first experiment was called the manure injection no-till experiment, and this was up in northern Vermont. You can see right on the Canadian border. And the goal here was to look at these different types of manure applications under no-till or vertical till, kind of reduced tillage, and measure carbon dioxide emissions and nitrous oxide emissions, as well as yield and protein concentrations of the crop. All right. Okay, so here's our first complicated slide, and really what we saw across 3 separate years was that manure injection increased nitrous oxide emissions. So the injected manure are the red lines and triangles, and we saw big, like sort of the biggest fluxes of nitrous oxide just following manure application. So that's what this dotted line is in the graph. So we have the dotted line, just following that, we would see these spikes in nitrous oxide across all the types. So we saw the biggest fluxes with injection. But you'll see after that, the remainder of the year, the types of manure applications didn't differ that much. So again, right, the manure is concentrated, pushing out air, adding moisture, lots of carbon and nitrogen. So we would see that flux of nitrous oxide or denitrification because of those conditions. Now, interestingly, you can see in 2016, nitrous oxide emissions themselves were quite a bit lower than the other years, and really that had to do with the conditions. It was much drier those years. So a wet season with injection, you do see more of a flux of nitrous oxide. All right, so hypothesis 1, we found that yes, nitrous oxide increased with injection, and those increases were much greater, especially when we were having wet years, and were the greatest following an injected applications, but then seemed to level out across the season. Things don't look slow. All right, we also had during that time a concurrent on-farm experiment that also looked at nitrous oxide from 2 large plots, one that was no-till and injection, and one that was conventional till with broadcast manure. So very similar to our replicated study, but on farm. And here again, we saw that manure injection increased nitrous oxide emissions, especially after spring application, which tends again to be wetter. And so the conditions are better for denitrification. Right, all my little things here. I also wanted to show you here the impact of warm wintertime temperatures. So you can see these little red arrows that say warm wintertime. And we would see nitrous oxide fluxes actually in January and at the spring thaw, with a large flux of nitrous oxide from injection in those injected watersheds. And so we were seeing these kind of post-application pulses, which was really interesting to us, that you could still pick up those differences in injected versus broadcast at certain times, especially when we would get these sort of thaws in the middle of winter or early spring. So that was new information, I think, for all of us. All right. So yes, nitrous oxide increased with injection, and now we also have new evidence of winter emissions, especially when the soils thaw. So during those winter thaws and in the early spring. So something we didn't know was occurring. All right. So then we got into, well, there's so many reasons to inject that are so beneficial. How can we be injecting manure and hopefully figuring out how to reduce the enhanced nitrous oxide emissions that may go along with that. So we thought about cover crops, and we have a lot of people cover cropping in Vermont as well. And could cover crops reduce nitrous oxide emissions by taking up excess nitrogen during that time of injection? So we thought that possibly that could be an answer for us. And so because so many farmers were cover cropping, we thought this was an excellent practice to look at to see if we could answer our question. So we started another experiment here, again at that same farm in Alberg, where we had in northern Vermont, right on the Canadian border, and we had spring and fall manure and incorporated or not. And then we had control plots where we didn't have any cover crops. And this is what we found. So again, we thought if we cover crop, the cover crop that was growing would take up that excess nitrogen when we put the manure down on the ground. But unfortunately, contrary to what our hypothesis was, the cover crop presence increased average nitrous oxide emissions by 50% times that relative to not having any cover crops. So you can see here the green is where there were cover crops present, and the red is where there were no cover crops. That line, that dotted line or solid line indicates spring or fall applied manure. And again, what you can see here is that the cover crops increased N2O emissions. So our hypothesis there was not correct. So this was really, a bummer to us. Very shocking, actually, and almost pretty disappointing to us. And again, if you think about it, carbon, nitrogen, you're basically adding a lot of energy, soluble nutrients to the system. And then you're adding more on top of that, having the cover crop. So it actually enhanced emissions. There was a lot of good news that we saw with this. And basically what we've been seeing is that NT, which is no-till, SM spring manure, FM fall manure, with and without a winter rye cover crop, it may be increasing nitrous oxide slightly over not having cover crop, but you can see the yield differences are substantial. So we are seeing 19 and 20 tons of corn silage when we have cover crops in the system, and 3 to 6 tons less when we don't. So this isn't to say that we should stop cover cropping or stop adding manure and doing these conservation practices, but we do indeed need to continue to figure out, how do we reduce these additional emissions that we're seeing when we're adding these great soil health and conservation practices to our systems. And here's just, a table showing the differences in soil health that we're seeing. All right. So far we know injection increases N2O emissions. NO and nitrous oxide increased when we added cover crops instead of decreased it. So now what? And this is when we started thinking about biochar. If we added biochar with the manure application, would we reduce nitrous oxide emissions? There is some support for this in the literature, not so much in field-based studies, but mostly in laboratory studies. And we thought, well, could this be a way to reduce emissions from manure applications? Okay, so again, benefits from biochar, you're have been shown to increase soil carbon, increase soil nutrient water retention, and in some conditions, decrease nitrous oxide emissions. So we set out to look at this. Can biochar added with manure reduce emissions? The sort of mechanism behind this is kind of unknown, but again, there is some theory that possibly the biochar acts as an electron shuttle, and it facilitates a transfer of electrons to soil, denitrifying microorganisms, which promotes a reduction of nitrous oxide to N2 instead of more nitrous oxide, maybe more N2 going into the air. But again, the mechanism here is largely not known yet and still being investigated. So I'll hurry up through my last project so we can get on to Debbie. So we had a biochar experiment, same site, and now we're looking at broadcasting manure and injecting manure, or just using urea-based fertilizers or nothing, no manure, no fertilizer, and all of those treatments with and without biochar. We did put the biochar down on the ground first, incorporated that into the soil, and then applied the manure or the fertilizer or nothing. And then we took our measurements, right? So you can see here, we have broadcast with biochar, without, the control, fertilizer, and then injection with and without biochar. And what we did find in 1 year, and this was an excessively wet year, that the biochar did reduce nitrous oxide emissions in injected manure plots and also in broadcast manure plots. But interestingly, in the fertilizer only plots, the biochar seemed to increase nitrous oxide emissions. But again, our primary concern was, or interest was, could the biochar reduce nitrous oxide with manure additions? And again, in this 1 year, it did. Okay, and then this is just highlighting the increase with fertilizer, which again, we're not entirely sure why this is happening. It may be because biochar adds carbon to these systems, and so you're actually getting a slight increase in nitrous oxide from that. But again, we don't know the answer to that yet. Very preliminary studies at this point. All right, we did not see any difference in yield of corn silage with or without biochar. So you can see in injected plots when we had biochar, we didn't really see much yield difference. And same with the other treatments. There was no significant difference on yields. All right, so can we reduce nitrous oxide emissions? We know injection increases it. At least in our studies, nitrous oxide increased with cover crops. But from our preliminary work at this point, biochar decreased nitrous oxide with manure applications, but a lot more to be studied here. I think that's actually my last slide. And I know we're going to leave time for questions, and I took my 25 minutes, a few minutes more than I should have. So I will turn it over to Debbie, and if you have questions, we'll put those in the chat and I'll try to answer those, and I think we'll have more time at the end.
Awesome. Thanks, Heather. And it's great to be able to build off of what you just presented on and really take a bit of a deeper dive into biochar and manure management. And thanks to Christine and Andrew for the invitation to present to you all today. And I'm going to run through a lot of slides briefly, but hopefully we do have some time for questions and discussion at the end, and I'd be happy to follow up with anyone on an individual basis after the webinar as well, because I'm going to cover quite a lot. And I will preface this, I am a soil scientist, but I don't particularly work on the manure side of things that much. I do a little bit of work, but I've really been focusing on biochar and compost. And within the biochar space for a bit over a decade now. So hopefully I'll be able to share some of that wisdom as it relates to manure management today. Before I get started, I just want to make everyone here aware of some resources that are freely available to you as it relates to biochar use in agriculture for applications to both annual and perennial crops. These are fact sheets that are available on the United States Biochar Initiative website. You can scan that QR code. These are just really practical, kind of down-to-earth extension publications that I helped develop when I was on the board of directors there, along with a lot of our partner organizations. So that one I want to highlight, and also a frequently asked question document that we put together with the USDA ARS, some of my colleagues out on the West Coast, to really answer some common questions around biochar. So just like to put those up front so people can have those immediately as resources in case I'm not able to answer all your questions today. So Heather briefly mentioned biochar and a study she and her colleagues had done in Vermont, but I want to take a minute and just explain a bit more about what biochar is. While a lot of people know what it is and are starting to use it, a lot of people still have no idea what it is and are hearing it for the first time. And so really it's a carbon-rich material made through pyrolysis. And so we're converting what are organic waste materials, and these can be any organic waste materials really prevalent within your region. Today, I'm going to be talking about biochar derived from manures as a waste product. And the idea is converting these within agriculture as a soil amendment. And so pyrolysis is essentially the heating in the absence of oxygen. And so biochar becomes one product that's produced along with gases and liquids that can be used for other applications. So we're really focusing on biochar as our solid soil amendment product in this presentation. So biochars span a range of carbon. They're mostly carbon. Hardwood biochars are about 90% carbon, whereas our manure biochars are around 50% carbon. But the idea is that they're incredibly highly porous. They have a lot of large and small pores, and they act like a sponge. One of the reasons for capturing things like greenhouse gases, as Heather alluded to earlier. And the real interest, I think, here within agriculture and thinking about manure management is that biochar degrades on very different timescales than our typical amendments that we think about. And so that pyrolysis process creates an incredibly recalcitrant or resistant to degradation material that, when applied to soil, lasts for hundreds to thousands of years. So that's really what's unique about biochar and sets it apart compared to other amendments farmers are used to working with: manure, compost, things like that. And so the amount of biochar that's used up pretty rapidly is about 50%, but then over time, about 50% of that biochar will remain for hundreds of thousands of years. And this is one of the motivations behind carbon credits and biochar being the main over about 80% of voluntary carbon credits sold on the market nowadays is because of that stability when it comes to carbon when applied to the soil. But the thing with biochar is that it's not just biochar, it's biochars. There's a great diversity of this material that leads to many different impacts. And this is one of the reasons that there's been a lot of questions and uncertainties around biochar and the variability when it comes to capturing greenhouse gas emissions and things like that. Obviously, it also has to do with heterogeneity in the soil or differences there. But we get kind of these soil by crop, by biochar, by climate or environment and management interactions that all lead to different results in various environments. So it's kind of like this idea that biochars are not created equal. They come in different forms, have different uses, and the impacts they have in any given environment can vary. And so this is this idea of site specificity around biochar has made it difficult to provide overarching broad scale recommendations to folks. And so we're getting, or I'd say the industry is really getting to the point where we can provide more general recommendations, and I'll share a few of those in some later slides. But this is really what has limited the adoption, because it's kind of it depends or site specific recommendations. And so I'm just putting this slide up there to give you some sense of the diversity of biochar materials that are on the market to you as a farmer or a technical service provider if you work with farmers. Everything from freshly produced raw biochars to really pelletized biochars, which can go through drills and other applicator equipment, granulator biochars, which can actually be like prilled urea products, blended biochars, which can be blended typically with compost or manure. And then we get our really pulverized liquid biochars that can be suspended within liquid manure, for example, or water and dispersed out on fields that way. So I'm going to talk a little bit about some work we're doing here in Central New York that I'm doing with my colleagues Johannes Lehmann and Lucinda Lee, looking at some manure management on a large New York dairy. And so this is currently how this farm, it's in Union Springs, New York, right on the east side of Cayuga Lake in the Finger Lakes region. It's about a 2,000 head dairy operation. And so their current manure management is, and this is typical, I'd say, of most New York dairies, is anaerobic digestion on that farm, and they have a large manure lagoon here. And so I've been working with Johannes Lehmann and Lucinda Lee on this dairy manure to biochar project, which is funded by our New York State Energy Research and Development Authority, really to get at, can biochar be created from dairy manure? And the big motivations around that being a waste volume and reduction, basically, and utilizing it as energy on the farm as well, and an adaptive approach to nutrient management on the farm. So this is just kind of big picture overview of it. Some of the benefits and challenges around carbonizing manure in general, and some that we've run into on this project. So some of the benefits, just to start with, is that we get tremendous reduction in the volume of manure by carbonizing it, reducing emissions, tremendous odor elimination, removal of harmful elements and compounds found within manure, and in some cases, not specifically to this project, but to others, getting carbon credits. Challenges, obviously, dairy manure is 95% water, basically, so significant moisture, and pyrolyzing that is difficult, but I'm going to show you the steps we go through to actually making that happen. The nitrogen gets tied up within the pyrolysis process, but that actually the phosphorus becomes more readily available once applied to the soil. So that can be real benefit in terms of supplementing synthetic or any synthetic nutrient use, but costs. I have a slide at the end. Biochar is expensive. Pyrolysis equipment is expensive. This has certainly been a large barrier to adoption of biochar use, I would say, in the US and abroad, anywhere in the world. Markets are still really in development, and there's a lot of work to create industry standards around biochar so there can be more uniform products and marketing of these products. So at this dairy in New York, basically I'm gonna show you just the process of starting with the animals to the liquid tank, there to the sand separation at the farm. And so we're right about 95% liquid here. And then the sands separate from the dry solids. And then we're down to about 65% moisture in the dry solids. The dry solids get fed into an auger there. And then the auger is, it dries and it gets fed into a pyrolysis, or let's say a kiln here, and we come out with about 2% moisture in a biochar product. So that's a really quick overview of how we go from that liquid manure all the way to a biochar. I will say this is a pilot scale. So we are only, or at this farm, it's only processing about 10% of the manure that the farm produces. There are significantly larger industrial scale systems out there that could produce biochar from 100% of the manure at this farm, but this is for research purposes. So I just want to be clear on that. But one of the main takeaways from the work that's happening here is basically, is it possible to convert dairy manure to biochar? And the answer is yes. And is it energy efficient and cost effective? And the energy story here that I'm quickly going to go through is obviously, as I said, about 95% moisture within the liquid manure. And by the time we get to that resulting biochar at the end, we've gone down to about 2% manure. So we have a lot of loss in that system, obviously, of the moisture. And what we see within this system is that there's over 95% reduction in mass of the dairy manure and 80% reduction in volume. So there's tremendous benefits there in terms of actually converting the product. From an energy consumption standpoint, we see that obviously there's a little bit of energy that has to go in to start the system, and the majority of that energy goes into actually drying the dairy manure. But the system also produces heat and generates energy that then could and ultimately would be fed back to heat the anaerobic digester, so you wouldn't have to use external heating for that. And you get a net energy balance that is very positive, that could be used, like I said, for the anaerobic digester or other places on the farm. So from an energy perspective, it is very feasible to make this happen and integrate it within a larger farming system. From a greenhouse gas mitigation standpoint, all the carbon in the manure decomposes into greenhouse gases. When it's pyrolyzed, only 30 to 50% of the carbon is volatilized into CO2 and methane. And then the remaining carbon, when applied back to the soil, so basically to the fields, it will persist for hundreds of thousands of years, like I said. And so the objectives within this study were, or are, to assess reductions in greenhouse gas emissions from manure management, and then substituting inorganic fertilizers with biochar-based fertilizer, this manure biochar fertilizer. And so within this figure here on the left, the red stars indicate where pyrolysis can reduce greenhouse gas emissions in manure management. As Heather mentioned, this is highly variable, but generally we see reductions within greenhouse gas emissions when it's added to a manure pile or to a crop field. The blue stars are areas where biochar can be used to filter the media, capture nutrients, reduce ammonia and nitrous oxide emissions. And then the arrows indicate the relative emissions amount there. And so overall, biochar application to soil can decrease methane emissions by 50% and nitrous oxide emissions by up to 38%. But once again, highly variable. This is some work that's happening. We are shifting from actually producing the manure biochar to beginning field trials this year at the farm. So some other applications of biochar within manure management or on a animal operation are within anaerobic digestion. This is some of the work that's been released in the literature that has looked at its use, reducing digestate volume more rapidly and greenhouse gas emissions within an anaerobic digester, enhancing the performance and the stability of the process, improving the quality and quantity of methane, reducing hydrogen sulfide levels within the biogas, producing a long-term carbon amendment that has more favorable, let's say, agronomic benefits than simply if the manure itself is applied. And this is summary here. Biochar within composting process itself. So reducing greenhouse gas emissions from compost process, specifically methane and nitrous oxide emissions. And so what I'm sharing here is things from the literature. This is not work that I've done specifically myself. So this is what is possible and feasible on operations. So just putting that out there. But improving nutrient efficiency so that biochar really binds up nutrients and makes it like a slow release fertilizer. So you get retention and availability of those nutrients over time. If you are using biochar within the composting process itself, it has been shown to accelerate the composting process and actually, so you get finished compost more quickly. And we're talking about only a 5 to 10% addition of biochar to a composting pile. So we're not talking about it becoming 50% or a significant amount of a composting pile. One of the greatest benefits with biochar, and a lot of studies have shown this across cropping systems, is enhancing microbial diversity and microbial activity. This is one of the reasons for speeding up compost production. We see reductions in volatile organic compounds and significant odor reductions, which is really one of the major benefits we see for manure management, is that the odor elimination. And like I said, capturing of nutrients and acting like slow release fertilizer once they are applied to the soil. There's also been a bit of work out there in different parts of the country of using biochar within manure lagoons and reducing, so basically having a bio cover with biochar. This bio cover is essentially floating on the surface of a manure lagoon, and some studies have seen reductions up to 80% of ammonia produced within these systems. That was one study. I'd say that's very much on the higher end, but I'd say overall it's been very positive in terms of its ability to reduce ammonia coming from lagoons. And like I said, odor elimination, I know there is a farm in Vermont that is using biochar within their manure lagoon as well, and they've been very happy with it from an odor elimination standpoint. Then once again, greater nutrient retention and kind of longevity once applied to the soil. And so I'm going to spend the rest of the time, I think the last 5 minutes I have or so, just to speak a little bit to actual field applications of biochar once it's used as a soil amendment. And this is the area I'm way more used to speaking about, and more of my work is involved in this area. So I really like to say that, biochar is not going to work on every farm. I like to be a realist about it, even though I think it's a great tool for farmers, but it's just another tool that's available for you. It might not replace things, but it's another option if it will work on your farm. And I say that with this idea of knowing why you're applying biochar, why you are utilizing it, what is the problem that it's trying to solve, because it's not a silver bullet. Like, nothing is a silver bullet. And so it's thinking about, why am I putting biochar into my system? What am I trying to get out of applying it to the soil? Am I looking to increase microbial activity, organic matter, alleviate compaction, improve water retention? We have a lot of heavy soils right in the Northeast. There are some pockets of sandier soils, but it's really thinking about, where will I get the greatest bang for my buck when it comes to applying biochar. So when I talk about biochar in terms of use within agriculture, it's taking a similar approach as the 4 R's of nutrient stewardship. And I think Whether you're in Canada or you're in the US, this is something all farmers are familiar with, or I hope you are, from the fertilizer industry. But thinking about the right source of the biochar, the right rate, the right place, and the right time. So the right time is way more important when you're talking about perennial cropping systems, less so when you're talking about annual cropping systems. And I'm just going to briefly cover each of these from an agronomic standpoint, but the right source, right? So this is what's local, available, and sustainable. We're talking about waste materials. Obviously, we're talking about potentially manure management and producing biochar from manure. And like I mentioned, there are industry scale producers making biochar from hog manure, poultry manure, dairy manure, and many other sources as well. So it really depends upon your industry. It depends on where you are. The right place, I'm gonna not explain this figure, but put the summary there, just again for the sake of time, that essentially when we're talking about biochar and thinking about really where we should be targeting applications to our fields as farmers, we're targeting lower quality soils where we have an issue with pH, where we have low soil organic matter, where we have low cation exchange capacity, or we have low ability to retain water. Or these are our sandier soils, so our coarser textured soils. So this is where we see from thousands of studies across the world where we would have a much greater benefit from a yield perspective when we applied biochar. So we're thinking about not applying necessarily biochar to all our acres, and certainly not our most productive acres, but thinking about where do we have a problem area in our field and where can biochar help us address that problem. And so I will say one thing when it comes to the pH side of things, this there are a lot of benefits when biochar is applied to acidic soils, and this is because biochar can act like an agricultural lime. It can replace ag lime in certain settings. And so there's a real boost because of the alkalinity of most biochars. And so this is another way to also take into account that biochars are more expensive than most other soil amendments, and particularly it's way more expensive than manure alone. So it helps cut down on costs when we're talking about strategic applications to fields. If you are in the US, I know there are some decision support tools available to help farmers in evaluating where you shouldn't be applying biochar to fields. There's a tool built into the USDA Web Soil Survey called the Dynamic Soil Properties Response to Biochar. And there's also a lot of work going into what's called what will be the National Biochar Atlas as well. A lot of the number one question I get from farmers is rate. How much do I apply? And I already saw someone had asked this question when Heather presented. How do I know how much to apply? If we could answer this question, I think the industry would be much further along than it is. It's the most difficult question, and I can never give someone an exact number of how much to apply, which makes it very difficult. But what I can say, and thinking about general ranges, more is not always better when it comes to biochar. We know there's a threshold at which you can actually get detrimental impacts of biochar. And so within all my field trials and field trials, I've seen where there's a lot of success and recommendations, I think, of leading researchers is I would never apply more than 10 tons per acre in a single application. Field trials, we have 8 large-scale field trials here in New York State on dairy farms now, and we're looking around the 3 tons per acre for a single application rate. So much lower than a lot of people think you need, and this also helps from a cost standpoint. So just thinking not necessarily more is better. It's a really it depends situation on your farm and where you're looking to apply biochar. So I generally provide ranges or an area to think about as a starting point, but really fine-tuning a specific application for your farm has to be done on an individual by individual farm basis. Right time, won't speak to the single application because that, like I said, is more relevant for perennial cropping systems, but for field crops, we can think about more repeated applications, maybe smaller annual applications, which helps from an economic standpoint and can also be better integrated into existing management practices when you're spreading manure, for example. I know I'm kind of right at time here, but I have a couple more slides left that I just want to show in thinking about the practical aspects of getting biochar out onto the landscape. Heather had pointed to the injection side of things. That can certainly be done. And there are many other ways that biochar can be applied depending upon the equipment that you have on your farm. And so the trials we're doing here in New York now are very much looking at utilizing the equipment that farmers have available to them to get biochar out on the landscape. I have two quick videos that I just want to show. So this is just a video of spreading wood biochar over a cover crop last fall here in central New York. This is on an organic operation. And so actually organic operations in the US, I don't know about Canadian laws, but in the US, if you are an organic grower, you cannot spread manure biochar or biochar derived from manure, but this is wood-based biochar. The next video I'm going to show is actually manure biochar being spread by a manure spreader. So I just wanted to share those videos so you have some sense that it can be spread very well through some common equipment that farmers have on their land. Just some other points and considerations if you're applying it to your fields. Applying biochar when it's not windy out, it's a very, unless you're integrating it within your liquid manure product, it can be a very dusty product and it can be blown around if there's high winds. So you really don't want to do it on windy days. And you want to minimize the risk of dust. You also don't want to be inhaling it personally. So any appropriate personal protective equipment could be valuable if you are applying it when it's slightly windy out, but definitely recommend it when it's not windy. And getting it incorporated into the soil, whether it's through injection or through a no-till drill or something, not just leaving it it on the surface, because it will leave your field through wind and water erosion if we get a heavy precipitation event after field application. Mixing it with mixing biochar with manure or compost or another nutrient source is much better than applying it on its own. We see a lot of synergistic benefits when it's applied with fertilizer. Biochar itself is not fertilizer. It's a soil amendment, so it's not replacing that fertilizer, but it can improve nutrient use efficiency. And this just makes it a lot more economical as well. Like I said, organic farms cannot apply manure-based biochar within the US. And I just want to wrap up by saying there are a couple other applications of biochar within the livestock industry. Use as a feed additive. So this is actually not regulated within the US and Canada. It's widely used within Europe as a feed additive, and it's being, I would say, looked at on a research scale here. I know there's some research happening here at Cornell looking at feeding biochar to cows to see if it helps reduce methane production from them. There has been some other work out west on this as well. But I do know there is a farmer somewhere in Ontario, maybe he's on this webinar right now, who has tried feeding biochar to his dairy cows and I think been quite happy with it. And actually, a colleague shared that this farmer had found better nutritional status and health of the cows, fewer abortions, and increased milk yield and quality. anecdotal. I'm saying that, don't hold me to it, but that was what one Ontario farmer had found. The other side of things is integrating biochar within bedding. And so that picture on the right there is actually sawdust and biochar blended as bedding, which can help decrease the moisture of bedding material that the cows are standing on. The final slide I have is around cost and availability, because everyone asks around economics of biochar. So biochar is available at the farm scale now. This was not true a handful of years ago. We didn't have industrial production of it. And I'm sorry, I'm speaking from mostly a US perspective. I know there are some suppliers in Canada, but in the US, I would say it's available at a farm scale. But I would say there's a large disconnect from those producing biochar right now and the farmers who need it or are interested in using it. And I say this because producers don't know how to connect with farmers, and the farmers are struggling to find the producers. There are some directories out there, but I think as this relationship gets improved, hopefully more farmers will be able to have access to biochar. The cost still is quite high, and definitely higher than just spreading plain manure or compost or something like that. I say you can find biochar for free. You can find it at $2,000 a ton, and this is US dollars. And so it can be very expensive. I would say the national average here in the US is around $500 a ton, but there's also a lot of people selling it more in the $1,000, $1,200 per ton. And the idea is the market continues to develop, the demand is there. Can this cost go down significantly? So that's kind of the idea moving forward. If you are a US farmer, once again, the USDA NRCS has funding available through the Conservation Protect or CPS 336, through EQIP, through various NRCS programs. So you can talk directly to your NRCS office. There are only 2 states in the US, North and South Dakota, that the NRCS do not offer this cost share funding. And that's for not just biochar, but all carbon amendments applied. Just a couple other points there. And I would just say sourcing local really helps keep the cost down on biochar, because about half the cost for biochar is related to transportation. So purchasing biochar from within 100 miles is economically a lot more favorable. Just wrapping up here, biochar, it's another tool in the toolbox for farmers, but it's not going to work everywhere. It is a long-lasting soil amendment. If biochar can be blended with manure or other nutrients, that's really the most favorable use of it. There are other benefits from a greenhouse gas emissions standpoint to adding biochar manure lagoons and anaerobic digesters, and also helping from odor reduction standpoint. Really thinking about how biochar could be incorporated into your existing management practices is going to be where biochar will provide benefit and be more cost effective. As more people are using biochar, the cost will continue to go down and the availability continues to increase. There's my email if anyone would like to follow up, because I just said a lot very quickly and I apologize. I did go over time, which I was afraid I would a little bit. And I see there are a lot of questions, so I will hand it back to Andrew.
All good. Stay with us here, Debbie and Heather, if you want to come online here. So many questions in the chat. And Heather, thank you. You have answered the majority of those. So what we're actually going to do is we will copy the chat and include it with the recording. So folks that haven't been able to see or watch that chat, you'll get those answers. We don't have to revisit them now. So thank you, Heather, for doing that. Some, Debbie, that were coming up while you were talking that I'll just throw at you right now. One of them, Deb asks about the typical nutrient content and pH of biochar. I know you said that really it's not a standalone fertilizer. Mix it with something else, but how about pH?
Yeah. So I will say first, from the nutrient standpoint, typically these have around 1 to 2% nitrogen. The manure biochars are more in the 5 to 7% phosphorus standpoint. So there's a little bit more nutrients within our manure-based biochars, but biochars themselves, particularly our wood-based biochars, are not a source of nutrients. Very, very minimal. pHs of biochars can range from 6 to 12, with the majority being, I would say, in the 8 to 9 pH range. But there are those extremes. You can do some post pyrolysis modifications to biochars to adjust the pH, but I would say the majority of just the biochar you could buy from a supplier is going to be in that 8 to 9 pH range.
Okay. Some comments in the chat about the fact that it's not on the list for an approved product for organic farmers. Any comments as to why, or is it just that testing hasn't been able to be done yet, or it's not consistent? Any thoughts on that?
So yeah, just to clarify what I'm saying there, it's manure-derived biochars that are not approved for organic operations. Wood biochars, rice husks, straw biochars, these can be used by organic operations. But according to the national organic standards within the US, you currently cannot use manure-derived biochars for application. So I do want to clarify that point, and that there's been a lot of, I think, education and outreach to try and say this isn't incineration, but I think there's a perspective that there's burning around this, and just some misunderstanding between incineration versus pyrolysis. So it has to do with the fact that for quite a long time, organics, they've tried to get away from ash and applications of ash on farms. And so they don't want burned manure. They would rather, manure applied.
Yeah, so. Got it. I do have to say, overall, I find this conversation fascinating, because I think back probably 25 years ago was the first time I ever heard of biochar. And at that time, it was so pie in the sky. It was like, you're a fruitcake if you're thinking about biochar. I mean, it was crazy. And it's just amazing how time has gone by, research gone by. I remember maybe 15 years ago, University of Western Ontario had a pyrolysis unit, and they were showing it. Last fall, I was in Ottawa, the National Research Canada site, and they had a unit working there. There's a lot of work going on. And as you say, it's almost like solar panels. Solar panels years ago, ridiculous. We're not going to see them on roofs everywhere. And now it's just the cost has come down, and it makes sense. And I can see that as you talk about the future and future costing, it actually starts to get kind of an eyebrow raiser.
Yeah, absolutely. I'd say, the industry has changed a lot in the last decade. It's grown tremendously. And the carbon markets are also changing the dynamics as well. But cost has come down significantly. I think as more people are aware of it, and thinking about it, realistic uses on their farm and how it could be integrated into their existing management practices, there's a lot more, I think, just potential for biochar to get out there. There's really been this huge research curve where we have over 30,000 scientific publications related to biochar, but adoption has still lagged. And so I think a lot of the work, Heather does with Extension in Vermont, that I do here in New York, and a lot of colleagues do around the country, has been really important to disseminate more realistic information around materials like biochar, which, could have, do have benefit, but you really need to be thinking about how you utilize it.
Right on. And thank you to Carl as well, who's been posting a lot of research papers in the chat also. There's one fairly technical question here in the chat, and I'll put it to you because you both have a bit of a soils background. This is from Ryan, two-part question. He's basically saying he's heard from an agronomist that if you multiply the soil CHC, cation exchange capacity number, by 10, you generally get the pounds of nitrogen per acre that a soil can hold. Is this a reasonable statement? Or is there a better method to get an estimated amount of N a soil can hold for a prolonged period? That's question one. Maybe I'll stop there. Thoughts on that? And if you want to take a pass because it's a pretty
I
technical one.
I have never heard that, so I'll let Heather take a stab
Yeah.
if she has any idea.
Yeah, obviously cation exchange capacity and the measurement of it is an indicator of the, ability of your soil to hold on to positively charged nutrients. I think it would be difficult to then use that number to think about any potential available nutrient values. But I think what they're asking really is the capacity of the soil, not necessarily if you would use CEC to make a recommendation. I think what they're asking is just like, does this help us understand the overall capacity of the soil to hold nutrients? And the answer to that is yes, but I've never seen a multiplication factor to determine like it can hold this many pounds of nitrogen. And then I wouldn't even know what that would mean because it's so much, everything is in flux in the soil depending on how much potassium is also there or calcium or aluminum. So I don't think it would be that valuable to know.
So in
I
relating
don't
it
know
to
if that's an answer, but
no. Hey, it's complicated. Let's just say that. It's very complicated and site specific as well. But relating it then to biochar, so is there a possibility
yeah,
here of biochar then increasing the soil's ability to hold
yes.
nutrients over the winter?
Yeah, absolutely.
So
Right.
yes to that. I think that's pretty
Yeah.
clear. And then he takes it further to then management. So could biochar potentially alleviate the need to do a split application of manure because of that? Because you've got that increased ability to hold those nutrients. Or is that pretty just theoretical?
So from the
Yeah.
go ahead, Heather.
Nope. You go.
I was gonna say certainly from biochar does increase soil cation exchange capacity, and it also has very high specific surface area that help retain the nutrients as well. And so it's a combination of surface area, porosity, and the exchange sites available. So certainly biochars help retain the nutrients and also, like I mentioned, act like a slow release fertilizer over time. I haven't done work specifically with split applications of manure and biochar applied at that time, but the idea would be that biochar hold onto more nutrients, and so then you don't need to. But a farm also needs to get rid of its manure as well, so I'm not sure exactly how that would play into it.
Yeah, and I mean, at least apply, the research we did was, I probably should have said like proof of concept. Is this going to work in the field? We used high rates of biochar that were not economically really feasible for any farmer, really. And I didn't show this, but we also did not see the same effect this year. So we're just digging through that data. And I think just like other tools that we have to reduce emission, like weather matters. Like if we were drier, are we going to suppress nitrous oxide activity if it's not there to begin with? Right. So it's the same with inhibitors. Somebody was asking about inhibitors, and inhibitors work, but they work when you have the conditions that promote volatilization of nutrients or various losses. So they're like an insurance. So I mean, there's still a lot to learn here. And I did see the reference that Carl shared at Ag PhD, and yeah, I mean, you definitely can look at it the way that publication shows, But again, yeah, I'm not sure that's really the right way for us to be thinking about how to manage nitrogen on our. It's complicated, as you said to begin with.
Yeah. Yeah. Fair enough.
Very complicated.
Well, listen, we could go on. This
Yes.
is a very interesting conversation. There's more to be said, but we've got to call it at some point. So we're going to call it
Yes.
there. Listen, Heather, Debbie, thank you very much. Appreciate the work you're doing. Appreciate your time to join us today. And to everybody online, thank you for joining us this year. We've had a great run. We will get these sessions posted and look forward to your feedback and ideas for next year. So
Right.
over and out for March
Thank you.
Manure Mondays 2025. Cheers, everyone.